In 1930, a 24-year-old observatory assistant named Clyde Tombaugh was assigned an incredibly tedious task. Night after night, he photographed the exact same patch of the Arizona sky, flipping back and forth between glass plates, looking for a single microscopic point of light that shifted its position against the fixed stars. When he finally found that moving dot, it became Pluto. For the better part of a century, that distant point of light held the title of the ninth planet in our solar system. Then, in 2006, the International Astronomical Union held a formal vote. They stripped Pluto of its planetary status, reclassifying it as a dwarf planet. Following that demotion, it was easy to file the world away as unimportant. Because it sat billions of miles from the sun, the scientific consensus and the public imagination settled on a simple conclusion: Pluto was a small, distant, and geologically dead chunk of ice. In 2015, NASA's New Horizons spacecraft flew past Pluto at over 30,000 miles per hour. After a long 9.5-year journey, the probe had exactly one chance to capture data before hurtling onward into the dark. It beamed back images of a massive heart-shaped plain, sprawling nitrogen ice fields, and towering mountains. For years, Pluto remained an assumption, a cold, finished story. That changed when a new generation of sensors began detecting atmospheric behaviors that a high-speed flyby could simply never capture. To understand Pluto's active chemistry without waiting decades to send another probe, researchers needed a way to read light itself. They needed a tool capable of breaking sunlight apart into its individual wavelengths, to reveal a precise chemical fingerprint from millions of miles away. Looking at this historical thermal data, you can see the technical wall earlier researchers hit. Pluto and its large moon, Charon, sit so closely together in the sky that their thermal signals merge into a single blurry blob. Isolating the heat signature coming from Pluto itself used to be practically impossible. That changed in 2022. Once the James Webb Space Telescope calibrated its highly sensitive mid-infrared instruments, it managed to cleanly separate Pluto's specific thermal fingerprint from its neighboring moon. What Webb sent back allowed researchers at the Paris Observatory to confirm a strange hypothesis published in 2025. Pluto's thin atmosphere is wrapped in a blue hydrocarbon haze. Instead of acting like a blanket to trap heat, this haze absorbs incoming sunlight during the day and immediately radiates that energy back out into the vacuum of space as infrared heat. The haze acts as a radiator, actively bleeding away what little warmth the dwarf planet receives. Because of this exact mechanism, Pluto's upper atmosphere sits roughly 30 degrees Fahrenheit colder than any of the early models predicted. We are observing a completely new kind of planetary climate. Pluto is cold because it orbits in the outer solar system, but it is also actively refrigerating itself. The sunlight reaching Pluto's atmosphere is 1,000 times fainter than what we receive on Earth. Even at high noon, the surface sits in a heavy, grayish-blue twilight. Yet even this incredibly weak trickle of solar radiation carries enough energy to break apart methane molecules suspended high up in the thin air. Those broken fragments then recombine into heavier, more complex compounds. This chemical cascade produces heavy, reddish-brown particles known as tholins. Drawn down by gravity, they form a slow, continuous snowfall settling onto the frozen terrain. Tholins belong to the exact same broad family of organic molecules that some researchers believe rained down onto early Earth, potentially providing the raw chemical building blocks that led to biological life. On Earth, that chemistry finished playing out billions of years ago. On Pluto, this process provides an active, natural laboratory, a continuous organic snowfall running in deep freeze for 4 billion years. The broken molecules don't simply settle on the surface. Pluto's weak gravity allows methane and other light gases to leak upward, escaping into the vacuum of space. This diagram maps where that escaping material ends up. Across 12,000 miles of empty space, Pluto's moon Charon catches the leaking methane. Because Charon experiences decades-long polar winters in complete darkness, the poles act as massive cold traps, freezing the methane solid as it arrives. When sunlight eventually returns to those poles, ultraviolet rays and cosmic radiation bake the frozen methane, reassembling it into heavy organic compounds and locking in permanent deep reddish-brown stains. The chemistry exchange goes even further. In October of 2024, Webb data confirmed the presence of both frozen carbon dioxide and hydrogen peroxide directly on Charon's surface, a specific combination of chemicals never verified there before. These two worlds are locked in a continuous exchange of atmosphere and chemical color, revealing a moon with a chemistry that contradicts its plain, icy appearance. Down on the surface of Pluto, temperatures generally hover near 400 degrees below zero. In this environment, water ice stops being slippery. It freezes so hard it behaves closer to solid rock, capable of ringing like metal if struck. Across the equator, New Horizons photographed towering, jagged blades made of solid methane ice. Arranged in long parallel ridges, some of these structures reach 1,500 feet into the hazy sky, forming a massive ring of frozen terrain circling the dwarf planet. Even more baffling are the isolated peaks rising south of the heart-shaped plain. Some of these mountains stand 20,000 feet tall. They feature deep central depressions and lumpy, uneven flanks that closely resemble cooled lava flows on Earth, except there is no molten rock here. Scientists classify these structures as cryovolcanoes. Instead of erupting with melted stone, they pushed up a thick, freezing slurry of water, ammonia, and methane from deep underground. For a cryovolcano to exist, something in Pluto's relatively recent geologic history had to be warm enough beneath the crust to force liquid material all the way up to the frozen surface. That internal heat points to the most debated theory in planetary science today. Researchers strongly suspect a massive liquid water ocean is buried roughly 100 miles beneath Pluto's icy shell, kept in a liquid state by the slow radioactive decay of elements inside its rocky core. This cross-section shows the evidence driving the theory. The specific alignment of cracks and ridges across Pluto's surface matches the stress patterns you would expect from a subsurface layer of water slowly shifting. Furthermore, that famous pale, heart-shaped plane sits directly above a concentrated gravity anomaly, suggesting a dense mass of liquid pooling underneath. If this hidden ocean exists, it has likely been there for billions of years. It offers an environment where the basic chemical conditions required for life could exist under enormous pressure, completely sealed away from the light of any star. To understand the true scale of this, we have to look past Pluto itself. It sits inside the Kuiper Belt, a vast, mostly unmapped ring of debris containing hundreds of thousands of icy bodies and trillions of comets. Pluto is likely not unique in its behavior. It is simply the only object in this deep space region that is close enough and bright enough for our current instruments to observe in detail. We used to think Pluto was the dead end of the solar system. Now it's a self-refrigerating world, leaking atmosphere to an active moon, with towering ice volcanoes and a potential hidden ocean. It leaves us with a massive question. If one dismissed dwarf planet holds this much complexity beneath the ice, what are the trillions of unobserved worlds in the outer dark hiding right now?